One, two, mic check. Yeah, just my volume has to be at this level. Okay, good.
Welcome, everyone. It is great to see you here on Sunday at the Cryosphere Pavilion at COP27. I'm happy to introduce our next speaker. He is one of our early career scientists at the Pavilion, and he will be here for week one. His name is Bimo Niraula, and he is a PhD candidate at the Alfred Wenger Institute through the University of Bremen, Germany. His research is centered around sea ice, and I'm very happy to give the floor to him.
Good. Thanks, Amy. Thank you for introducing me. As you said, I'm Bimo Niraula, or just Bimo, and I'm a research associate at Alfred Wegener Institute in Germany, and also a PhD candidate at the University of Bremen. And yeah, I'm very happy to be here at COP27, to be meeting all the people and to be listening to some great early career scientists, as well as to find out more about the delegations and how the negotiations take place. My own research is focused on sea ice, especially the sea ice edge. And I'll come back to why there's a little asterisk on the edge part, but I'd like to start with this little video, if it works. And well, it doesn't work, so you just take my word for what it shows. It shows the evolution of sea ice in the Arctic over the winter 2021-2022 period. And it shows you how sea ice is a very dynamic layer on the ocean surface. And it is moving fast in some regions, it is very stable in some other regions. But you can also see that there are little pockets opening up here and there. And it's very important in the Arctic climate environment because in the Arctic climate, because of a multitude of reasons. Most importantly, it is a very good reflector of sunlight. So we call this the albedo effect. And it is also important in how it balances the upper layer of the ocean. So because of the way it freezes, there is like a halocline layer. The salt runoff is stored in this layer, and that modulates the ocean temperature. So it's a very important part of the Arctic climate. And as you've already heard before, and you'll hear more about it later, over time, the extent of sea ice, how far it goes in the winter or in the summer, is slowly decreasing. And that's a very big problem, not just because of the albedo effect, but also because of how it affects the coastal communities, especially in the Canadian basin. Sorry. Okay. So we're also seeing so how do we actually observe and how do we actually study sea ice? So mostly a lot of what we do is using satellite images. Here's a sample from the AMSR satellite where we're seeing the sea ice condition in October 11, 2022 in Antarctica. So you see how it is distributed. And it's expressed in terms of sea ice concentration. This is the scientific unit that we study in it. It's basically how much of the grid how much of the unit is covered with ice. We also look at it in reanalysis data. So this is data that has been reprocessed to kind of cover everything that we have. And also in terms of forecast. Sorry, there's a slide missing here. And one of the important factors in regards to sea ice is this concept of ice edge, so which is the effective border of ice presence. Generally, if we're using a concentration, it's like the contour of the threshold, which is very important for marine and operational needs. So if you're taking a boat out north and you want to know where the ice effectively begins, And it's also very important for safety planning reasons, because every winter there are multiple trips to the north to supply remote communities, and they need to know whether or not they can be accessed in time. It's also important as a climate marker. So here we see on the right hand side a comparison of the sea ice edge between 2019, March 2019, and the long term mean from the previous 20 years. And you see the reasons where the ice edge has shifted substantially, especially between Greenland and Svalbard. And you see in the Pacific opening, there has been a big movement of the ice edge. In some reasons, the ice has also moved forward a bit due to small regional effects. But when you look at ICES, both in observations and in forecasts, what we need to know is how can we verify its accuracy? How can we tell if it's accurate or not? So for this, we use a bunch of verification metrics. One of the important one is called integrated ICES error, where we have two ice edges, one from the forecast. Let's say the red one is from the forecast and the blue one is from the observation. So then you add the areas of over forecast and under forecast in and this has been used for a lot of forecasts, whereas now we're moving on towards concept of ensemble forecast, where people are producing forecasts with the same initial condition but producing them multiple times, so you get a range of outputs and you can have a probability of things happening. So in the figure you can see the probability of ice presence with this color bar, and then the observation is shown by the red. So you can use the difference in probability to determine the spatial probability score. So these are things that I'm using a lot in my own research, as you'll see further in this presentation. And another important concept is this idea of subseasonal to seasonal forecast. It's otherwise known as S2S forecast, where we're predicting ice presence not in the current or the next few days term, and not in long-term climate projections, but between weeks and months. We're using this ensemble forecast that I just described, and this is being done with dynamical sea ice models by different Met offices and meteorological centers. So in prior research, we've kind of used these tools of spatial probability score to assess how accurate the forecast from these different meteorological centers are. So here we see the comparison for a bunch of different operational centers. And there are two references we use, which is climatology, which is written by Klim, and persistence, which is shown in this line over here going up. And we see that most of the operational centers, they're all using a good chunk of my research is looking at this method of spatial damped anomaly persistence, where we combine initial and present conditions against historical probabilities and use the anomaly to predict how it's going to be in the near future. Maybe I'll just briefly go through this, where we take if we have a probability and a climatology, so the historical probability, then we can take the initial observation in the first day and use it, inherit it throughout your field to kind of project it on the future date, and use this to make a forecast of the ices. And this gives a very deterministic or like a sharp forecast, but we care in operations about having a probability forecast, so we can use empirical damping to move it towards historical levels using different damping factors. And what we see from this is that this figure is a little difficult to read here, but what we see is that the forecast that we produce from this method, which is shown by the black line, is producing better than historical forecasts, better than climatology or historical forecasts, which is shown by the gray line. And if you remember the previous figure, we had most of the models were above the gray line. So we're doing better than a lot of the operational models using a very simple method. for every month we can have a different comparison of how our ice performance is doing. And sorry, there's a big lag between. I think the computer is frozen. I think the computer is frozen. No, I don't see it move. It's not moving. It's not going back and forth. No, that's fine. This is cool. Thank you. Yeah. Cool. Yeah. Sorry about that. So, it's frozen again. Sorry, I have to restart. I'll start from middle. Okay, cool. Yeah, thank you. Sorry. So, okay, I'm going to skip a few slides and start from here. We're saying that we're producing with a very simple method, we're producing these forecast of sea ice, which are better than most of the operational models. And this is very useful for in the field action when we need sea ice forecast for weeks ahead for planning or safety purposes. Another part of my research is on measuring observational uncertainty, essentially how well do different observational estimates of sea ice edge measure against each other. We're comparing between different data sets one-to-one. So we have a ORAS-5, which is a reanalysis data set, OCS-SAF, which is an observational satellite-based data set, and we have a bunch of different ones, similar satellite-based data sets. We have IMS, which is a data set that is produced by people actually marking things where there is ice or no ice, although it only exists in the Arctic. We're doing one-on-one comparison between these data sets in terms of these previous metrics that I mentioned, integrated ICES error. And we see that there is a lot of difference between satellite data sets for the same date, so much that sometimes it is as high as climatological error, or error if we just assume that the past is going to stay fixed. Cool, changing, thank you. Yeah, so so essentially this is the same figure we saw before. And okay, so I'm just gonna talk without slides, that's fine. Yeah, so we're making a lot of comparison. It's working now. We're comparing different satellites against each other, and we see that there are differences between the satellites in how much sea ice they're seeing in the Arctic for the same date. These differences are caused by minor issues in the algorithm or the use of different sensors on different satellite platforms, even though they follow the same basic principle. Most of the difference, if we take a seasonal mean, so we're just averaging over all the years, we see that most of the difference is in peak summer when there is more melt in the Arctic. So there are more melt ponds, or there are more open water areas. We can see which satellite-based data set has a higher estimate and which one has a lower one. Or we can see how they're biased against each other. This is the mean bias between some different satellites for the month of July. And we can also use all of these data sets to create a probabilistic measure where we like combine them to see what is the probability of ice presence on that certain given day, which is, they should all be agreeing, but in certain parts they do not agree. So here we see off the coast of Greenland, where only one of them said there is going to be ice, the other said there will be no ice. And we can use this probabilistic data set to measure the spatial probability score, which is essentially saying how inaccurate this satellite-based data set is. But even though they have some difference in between each other, overall, they all show the same thing, that there is a strong decrease in Arctic sea ice extent. This for the month of September, and all of the data sets agree that there is a strong decrease, which is like falling off a cliff edge. This is also shown in other terms. For example, here we can see the loss in terms of ice edge. So you see that the ice in the Arctic is getting newer, and when sea ice is old, then it survives much longer, it reflects more sunlight, it has different properties, and when it is younger, it melts off within the summer. So this is an area of huge concern, as we've heard from Arti already. So just to wrap it up, okay, that's fine. Yeah, I want to thank you all for this presentation, and thank you to International Cryosphere Climate Initiative for bringing us all here and making us a part of this COP event. Thanks to my collaborators, and I'm happy to take any questions.
Thanks, Bimo. That was really interesting, and well done for struggling through the technical issues there. You mentioned that the melt ponds on the ice can make it harder to edge. So is this a problem you foresee in the future when we have less sea ice to look at harder? It's going to be harder to get an idea of where the ice edge actually is.
Yeah, this is actually a really big problem, because the melt season is actually getting larger and larger. So we're seeing more melt ponds even in the fringe seasons, so early spring or late fall. So this is definitely going to be a bigger issue that we need to face off. That's why also these verification tools are important, so that we know when to assume that it's wrong and when to be sure that it's right. Once again, sorry for the technical issues, and thank you for your time.